This video will continue our travels through molecular geometry, and in this one we're actually going to deal with molecular geometry. Molecules do have a 3D structure. This is based upon the valence shell electron pair repulsion theory, or VSEPR theory, which states that molecules are at a lowest energy state when they have their electron pairs as far apart as possible from each other. So we have to start with defining what is an electron domain. There are two types. There are non-bonded pairs and then any type of bond. So a single bond, a double bond, and a triple bond are all considered one electron domain. Then you have to look at the 5 types of electron domain geometry. 2 domains is linear with bond angles of 180 degrees. 3 domains is trigonal planar at 120 degrees between the electron domains. 4 domains is tetrahedral at 109 degrees. 5 domains is trigonal bipyramidal. The equatorial domains are 120 degrees apart. The axial are 90 degrees from the equatorial. And then 6 domains is octahedral, and all domains are 90 degrees from each other. And here is a visual representation of what they look like and why you can see they're called pyramidal or tetrahedral. Now, the molecular geometry is derived from the electron domain geometry. There are 4 steps. The first, draw the correct Lewis structure. The second, count the number of electron domains. Then determine the number of bonding domains, and then refer to the memorized VSEPR chart. Yes, you must memorize the VSEPR chart to figure out the molecular geometry. However, to make life a little easier, if the number of bonding domains equals the number of electron domains, then the molecular geometry and the electron domain geometry are identical. So here is the start of the VSEPR diagram. If you have 2 bonding groups, you're linear, 180 degrees, and carbon dioxide is the classic example. Then you go to 3 electron domains. If you have 3 bonding domains, then since the electron domain geometry is trigonal planar, the molecular geometry will be trigonal planar, and boron trifluoride is a very good example of this. You could have 2 bonding domains and 1 non-bonding domain. The electron domain geometry remains trigonal planar, but now the molecular geometry is bent. Sulfur dioxide is an example of that. Then you go to 4 electron domains. If you have 4 bonding groups, then the electron domain geometry will be tetrahedral, as will the molecular geometry. And the example here is methane with bond angles of about 109 degrees. Go to 3 bonding domains, 1 non-bonding domain. Even though the electron domain geometry is still tetrahedral, the molecular geometry would be trigonal pyramidal, which means that the bond angles will be less than the electron domain angles, so it would be less than 109.5. Probably around 107 degrees, and ammonia is the classic example for this. And then last, you could have 2 bonding domains and 2 non-bonding domains. So your electron domain geometry remains tetrahedral, but you now have a bent molecular geometry. These bond angles are even less than the trigonal pyramidal, and you have water being the classic example. If you go to 5 electron domains with 5 bonding domains, then once again the electron domain geometry and the molecular geometry are the same at trigonal bipyramidal, and phosphorus pentachloride is a good example of that. You could have 4 bonding domains and 1 non-bonding domain, and now you get what is called the seesaw geometry, where the bonds are a little bit less than 120 degrees in the equatorial and a little bit less than 90 from the equatorial to the axial. You could have 3 bonding domains and 2 non-bonding, and this would be T-shaped, and all of the bond angles would be slightly less than 90 degrees. And lastly, you could have 2 bonding domains and 3 non-bonding domains, and now you end up linear with the 2 bonded atoms to the central atom being in the axial position. Next is 6 electron domains. If you have 6 bonding domains, then electron domain geometry and molecular geometry are the same, octahedral, all angles 90 degrees. 5 bonding domains, 1 non-bonding domains would be square pyramidal. And last is 4 bonding domains, 2 non-bonding domains, and you get square planar and the bond angles would go back to 90 degrees. So here are some examples. What is the molecular shape of phosphorus trichloride? Stop, figure it out, then I'll give you the answer and walk you through it. Go. And the answer is trigonal pyramidal. First thing you do is draw the correct Lewis structure. Next, count the number of electron domains. There are 4. Determine the number of bonding domains. There are 3. Refer to the memorized Vesper chart to figure out the molecular geometry. So here's the chart. We can see that with 4 electron domains and 3 bonding domains, that the molecular geometry is trigonal pyramidal, and so it would look like this. Another example for you to do. What is the molecular shape of tellurium tetrachloride? Stop, figure it out, come back, I'll walk you through it. Go. And the correct answer is seesaw. We start by drawing the correct Lewis structure. Count the number of electron domains, and there are 5. Determine the number of bonding domains. There are 4. Go to the memorized Vesper chart to figure out the molecular geometry. And with 5 electron domains and 4 bonding domains, you get the seesaw structure, and it would look like this. Now you do need to know the bond angles. If the bonding domains equal the electron domains, then the bond angles will be the same as the electron domain angles. If the bonding domains do not equal the electron domains, then the bond angles will be less than the electron domain angles. We have methane, which has 4 electron domains and 4 bonding domains, and the bond angles are 109.5 degrees. Take a look at ammonia, which has 3 bonding domains and 1 non-bonding domain. Even though the electron domain geometry doesn't change, you notice that the bond angles are slightly less. And this trend continues with water, where you have 2 non-bonding domains and the angle is even smaller. And the question is, why does that happen? Well, it turns out that non-bonded pairs are more repulsive than bonded pairs because they have a higher area of negative charge. That pushes the bond angles further away from the non-bonded pairs, and so closer to each other. And if you're asked that question on the AP exam, you need to specifically mention the greater repulsive effect of the non-bonded pairs. So to review, molecular geometry is derived from electron domain geometry. Don't forget the 4 steps. Got to have the right Lewis structure. Got to count the number of electron domains. Then determine the number of bonding domains. And then go to your memorized Vesper chart to figure out the molecular geometry. If the number of bonding domains is the same as the number of electron domains, then molecular geometry and electron domain geometry are the same. If the number of bonding domains is the same as the number of electron domains, then bond angles and electron domain angles are equal. If the number of bonding domains is less than the number of electron domains, then the bond angles will be less than the electron domain angles. And that's because of the increased repulsive force of the non-bonded electron pairs, because they have a higher negative charge area. We have one more video on molecular geometry, and then that will wrap up this section.